Every atom in your body was once part of a star that lived and died long ago. That's not poetry, it's science. The stars above aren't just beautiful, they're the reason we exist. We are literally made of star stuff. Ancient civilizations worshipped them. Today, we know stars are born, they burn, and they die in explosions so powerful they reshape galaxies. So when you look up tonight, ask yourself, what are you really seeing? A light show, or the history of everything? Let's uncover the life and death of the stars and why their story is also ours. The birth of a star. Stars are born in the cold, dark expanses of space within massive clouds of gas and dust known as nebulae. Imagine these nebulae as vast cosmic nurseries where the ingredients for new stars are scattered across the universe. These clouds contain the raw materials, hydrogen, helium, and dust particles, that, when compressed under the immense force of gravity, can give birth to something incredible. Gravity is the star's first catalyst. It slowly pulls the gas and dust together, causing the particles to collide and condense, making the cloud denser and hotter. This process takes thousands to millions of years, depending on the size of the nebula. As the gas and dust compress, a new hot and dense core forms at the center called a protostar, but it's not quite a star yet. The protostar is still in the process of gathering mass and energy. The temperature and pressure inside this core continue to rise, and once they hit around 15 million degrees Celsius, something incredible happens. Nuclear fusion ignites. This is the moment when a star is truly born. Hydrogen atoms in the protostar's core start to fuse into helium, releasing vast amounts of energy. This fusion creates light and heat, causing the star to shine brightly. And just like that, a new star is lighting up the cosmos. The process continues, and as the star stabilizes, it enters the main sequence phase, which can last for billions of years. Stars may begin from the most ordinary of elements, but through the forces of gravity, pressure, and time, they evolve into shining beacons in the night sky, marking the birth of something far greater than just light. It's the beginning of a stellar life cycle that will span millions, sometimes billions of years. Main sequence. After a star is born and nuclear fusion takes hold, it enters what we call the main sequence phase. This is the star's stable period, where it spends the majority of its life. Think of it as the star's middle-aged phase, where everything is calm, stable, and most importantly, shining. The star is constantly fusing hydrogen atoms into helium in its core, a process that releases an incredible amount of energy. This energy is what powers the star and gives it its brilliant light. For a star like our Sun, the main sequence lasts for about 10 billion years. That's right, a star is in this phase for a very long time. During this phase, the star has reached a perfect balance. On one side, the energy produced by nuclear fusion creates outward pressure, which tries to expand the star. On the other hand, gravity pulls inward, trying to collapse the star. These two forces, gravity and fusion, counterbalance each other perfectly, keeping the star stable and glowing. For most stars, this is the longest period of their lives. They shine steadily, providing light and heat to their surrounding planets, and if they're lucky enough, they might even give rise to planets with life, like Earth. The main sequence is an incredibly important phase in the life of a star. It's during this time that stars reach their full luminosity, and for us on Earth, it's what allows the stars in the night sky to shine brightly. But just like every good thing, the main sequence phase must eventually end. But before we dive into what happens when the star runs out of fuel, let's just take a moment to appreciate this balance that makes stars like our Sun such essential players in the cosmic drama. This phase represents the peak of a star's vitality, and without it, the rest of the stellar journey wouldn't even be possible. Red giant phase. As a star like our Sun enters the later stages of its life, its hydrogen fuel in the core begins to run low. But don't think that means the end is near. This is just the beginning of one of the most dramatic changes a star will undergo. When the hydrogen runs out, the core starts to contract under gravity's pressure, and in response, the outer layers of the star begin to expand, cool, and take on a reddish hue. Welcome to the red giant phase, where the star grows into a colossal, glowing sphere. At this point, the star's core is much hotter than before, which allows the fusion of heavier elements like helium. As helium atoms fuse together, they form carbon and oxygen, and the fusion process generates even more energy. This energy causes the outer layers of the star to expand massively. In fact, a red giant can grow to be hundreds of times the size it was during its main sequence phase. If our Sun were to go through this stage, it would expand so much that it could engulf Mercury, Venus, and even Earth. Imagine our planet, once teeming with life, now being swallowed by a massive red-hot ball of gas. But even as the star swells in size, things are beginning to change beneath the surface. The increased temperature causes the outer layers to become unstable, leading to massive stellar winds that blow away the star's outer material. In some cases, these winds can carry away up to a third of the star's mass. As the star grows, it starts to shed its outer envelope, leaving behind a dense core. This core will eventually become what's known as a white dwarf, the next phase in the star's journey. While this red giant phase might seem chaotic, it's actually one of the most fascinating stages in a star's life. The transformation from a stable, burning furnace into a massive, unstable behemoth is an awe-inspiring sight. And it's during this time that some stars make their most significant contributions to the universe, creating the heavier elements needed for future star systems and planets. Supernova Explosion. For stars that are much more massive than our Sun, the red giant phase is just the beginning of a fiery and explosive end. These stars, once they have exhausted their core hydrogen, undergo a more dramatic and intense series of events that lead to the birth of one of the most magnificent phenomena in the universe, the supernova. But how does this happen? It all starts when the core of a massive star starts fusing heavier elements like carbon, neon and oxygen into even heavier elements like iron. However, when the core finally forms iron, something changes. Unlike lighter elements, iron cannot undergo fusion to release energy. This creates a major problem for the star. Without the energy from fusion to counteract gravity, the core begins to collapse. The pressure from this collapse causes the outer layers of the star to implode inward at incredible speeds. As the outer layers crash into the dense core, they are thrown outward in a cataclysmic explosion. This is a supernova, a violent, explosive event that releases more energy in a single burst than our Sun will release throughout its entire lifetime. The explosion is so powerful that it can briefly outshine an entire galaxy. During this brief period, the supernova becomes the brightest object in the sky, visible across vast distances. These explosions scatter the star's outer layers into space, enriching the interstellar medium with heavy elements like gold, uranium, and iron. Elements that are crucial for the formation of planets, life, and everything we see around us. Supernovae are essentially the universe's recycling process, creating new building blocks for future stars and planetary systems. But not every star dies the same way. While smaller stars will collapse into white dwarfs, the most massive ones undergo an even more fascinating fate: a neutron star, or, if the mass is great enough, a black hole. But before we delve into these stellar remnants, let's pause and appreciate the sheer cosmic power of a supernova. It's a spectacular end to a star's life and a beautiful beginning for the next generation of stars and galaxies. Stellar remnants. When a massive star explodes in a supernova, it doesn't just disappear into nothingness. What's left behind is a dense, compact remnant that is often more fascinating than the explosion itself. The fate of this remnant depends entirely on the mass of the star's core. There are two possible outcomes for the surviving core: a neutron star, or, if the core is heavy enough, a black hole. Neutron star. For stars with a core mass between roughly 1.4 and 3 times that of the Sun, the core doesn't collapse into a black hole. Instead, it becomes a neutron star, a celestial body so dense that its atoms essentially collapse into neutrons. A neutron star is incredibly small, with a radius of only about 10 kilometers, yet it packs more mass than our Sun. This density means that the star's gravitational field is extreme, and neutron stars are known to emit intense magnetic fields and fast-spinning beams of radiation, which we detect as pulsars. These pulsars can spin up to several hundred times per second, creating a cosmic lighthouse effect. Imagine the power of a star compressed into such a tiny, dense object. For stars with a core mass greater than about 3 solar masses, no amount of pressure can prevent the collapse. The core continues to shrink, becoming so compact that it forms a singularity, an infinitely small point with immense density. This process creates a black hole, a region of space where gravity is so strong that not even light can escape. A black hole doesn't suck everything around it like in the movies, but its gravitational pull is so strong that anything that ventures too close gets pulled in, never to escape. Black holes are mysterious and elusive, but they play a crucial role in shaping galaxies, as most large galaxies have a supermassive black hole at their center. These objects are both fascinating and terrifying, and we can only begin to imagine the mysteries they hold in the depths of their gravity wells. White dwarfs. While the fate of massive stars is marked by dramatic explosions and mysterious remnants, the path of smaller stars, those with less than 8 times the mass of our Sun, is equally fascinating but less violent. Instead of blowing up in a supernova, these stars end their lives as white dwarfs. For stars like our Sun, the transformation into a white dwarf is a quieter, more gradual process, but no less important in the cosmic cycle. When a star like our Sun runs out of hydrogen fuel in its core, it begins to shed its outer layers, releasing a glowing shell of gas and dust known as a planetary nebula. What's left behind is the core of the star, which becomes the white dwarf. A white dwarf is a small, dense object about the size of Earth, but with a mass comparable to that of the Sun. This incredibly dense remnant is made primarily of carbon and oxygen, supported against further collapse by electron degeneracy pressure, a quantum mechanical force that arises from the Pauli exclusion principle. In simple terms, this pressure prevents the electrons in the white dwarf from being squished together. Over time, white dwarfs slowly cool and fade, becoming dimmer and dimmer over billions of years. Eventually they will no longer emit any light or heat, leaving behind a cold, dark relic of the once glowing star. These white dwarfs are not completely lifeless though. In fact, the elements they contain are some of the building blocks for new stars, planets, and even life. The cosmic recycling process continues as the white dwarf's remnants, its carbon and oxygen, might eventually become part of a future generation of stars or planets. Even in death, the star has a profound impact on the universe, passing on the elements needed for new life to take shape. Stars with lower mass end their lives not with a bang, but with a whisper, a slow, silent fade into the cosmic background. But even in their quieter demise, they play a vital role in the ongoing creation of the universe. The cosmic recycling. The death of a star, whether through a supernova explosion, the slow fading of a white dwarf, or the quiet collapse of a neutron star, is not the end of the story. In fact, it's only the beginning of a new chapter in the universe's vast and ongoing cycle of creation and destruction. The elements that were once forged in the heart of a star, hydrogen, helium, carbon, oxygen, iron, and more, are scattered throughout space, enriching the interstellar medium and becoming the building blocks for the next generation of stars, planets, and even life. When a massive star dies in a supernova, the explosion blasts these elements into space at incredibly high speeds, often faster than the speed of light. This cosmic spray of material can travel across vast distances, carrying with it the very elements that are essential for the formation of new stars and planets. For example, our own solar system was likely formed from the remnants of earlier supernovae. The heavy elements that make up the Earth, including the iron in our cores and the oxygen in our atmosphere, were born from the death of ancient stars. Without these stellar deaths, life as we know it would not exist. But it's not just supernovae that contribute to this cosmic recycling process. White dwarfs, the remnants of medium-sized stars, also play a role in this cosmic game of life and death. Over time, as white dwarfs slowly cool and fade, they might still release their residual elements into the surrounding space. These elements could be incorporated into new star-forming nebulae, further fueling the creation of new stars and planets. Moreover, neutron stars and black holes, while seemingly the ultimate end for a star, are not entirely disconnected from the cycle of stellar creation. For example, neutron stars can emit strong bursts of radiation known as gamma-ray bursts, one of the most powerful phenomena in the universe. These bursts of energy can trigger the formation of new stars in distant regions, essentially reigniting parts of the galaxy into new life. Even black holes, with their immense gravitational pull, can influence the formation of new stars by pulling in nearby gas and dust, providing the necessary material for star formation in a process known as accretion. Thus, the death of a star is not a solitary event, it is an essential part of a greater cosmic cycle. Each time a star dies, it releases the ingredients for new beginnings, new stars, new planets, and potentially even new life. The universe, it seems, is forever recycling itself, and each stellar death is a crucial step in this ongoing process of creation. The birth and death of stars are, in a sense, two sides of the same coin, forever linked in the vast, ever-changing tapestry of the cosmos. Thanks for joining me on this incredible journey through the life cycle of stars. From their dramatic births in swirling clouds of gas to their spectacular deaths that seed the universe with new elements, stars truly shape everything around us. The next time you look up at the night sky, you'll see more than just points of light. You'll see stories of creation, destruction, and cosmic rebirth. Stay curious, keep looking up, and keep wondering about the vast universe we call home. And if you love discovering the secret of the universe, don't forget to like, subscribe, and hit the bell icon for more adventures.